It's now time to look at the power delivered in AC circuits. And so to start, what we're going to do is once again come back to our RLC circuit where all of our elements are in series. And we're going to remind ourselves that the um, voltage signal from the source is sinusoidal. And going back to our phasor diagrams, okay, so remember that the voltage across the resistor and the current are always going to be in phase, right? And so before I guess we get into the phasor diagram, let's just remind ourselves that at its essence, power is equal to IV, okay? Um, and so what we're going to be doing for our resistor, our capacitor, and our inductor, we're going to be taking the time average of this quantity I times V to calculate the averages. Okay, but the resistor and the voltage across the resistor, I should say, and the current are always going to be in phase. So what that means is if my current, okay, um, has this form of where we have the phase factor in here, or once again, remember that our phase factor is the difference between our reactances divided by the resistance. Take the tan inverse of that. Um, and so if I want to calculate the power, the average power, okay, now so remember this is the average. And the reason we're doing the average is because this is a sinusoidal signal, okay? So if P equals IV and my current is equal to this sinusoidal signal, then for the resistor, that must also be the form of the signal for the voltage across it because these are in phase. So wherever my sinusoidal signal is for my current must be in phase with my sinusoidal signal for my resistor, the voltage across my resistor. So if I want to calculate the average power for the resistor, okay, so once again, this is going to be IV, so this is going to be I naught sine omega t minus phi times V naught sine sine omega t minus phi. And because these are signals, we need to take the time average. So we do our integral over one period and then divide by the period. And so this becomes, I can pull out my I naught and my V naught since they're constant. I need to add my dt there, and this becomes sine squared of omega t minus phi dt. And we've already seen what this integral is. This is just 1/2 of the period. And so the average power dissipated by the resistor or delivered to the resistor, however you want to look at it, is going to be the product of my peak voltages and currents divided by 2. Okay? So that is where this expression comes from. That's how you calculate it. For a capacitor, okay, so remember that the capacitor, the current leads the voltage by 90 degrees, okay? So what happens for the capacitor is, let's see, so I is going to equal I naught sine omega t minus phi. And my voltage across the capacitor would be the cosine of this. Actually, let's come back here. So yeah, my current is okay. If we call the voltage the sine function, then the current is going to lead that by 90. So it'll be yeah, yeah, yep. Okay. So let's write that out like this. Oh. That's going to be fine. The bottom line is that with all of the shifting, it doesn't matter which is which. Okay, the current through the resistor is going to be a set value, but you could just as easily write them like this instead of writing the current as sine omega t plus pi over 2. You can shift the current and leave you can shift the voltage as the cosine function. And what happens now, okay, the point being that these are just shifted by 90 degrees. Okay, that's really the bottom line. And so the power through the capacitor, if we do the same calculation, the time average, where the arguments are the same, we need our dt. Okay, this calculation is 0. All right. And therefore, okay, there is no average power delivered to the capacitor. So what this means is that sometimes the capacitor is absorbing power and sometimes the capacitor is delivering power. And one way of thinking about this is if I look at this graph, okay, look at this graph, and you'll notice that the product of V and I, let me see how finely I can draw this. So right here is where your current dips below 0 the first time. So everything here in this shaded region, if I multiply V and I, then I will get a positive value. But then, while my voltage is still positive and my current is negative, let's use light blue. From here to here, okay, that condition is met. Now this product is negative because my voltage is positive, my current is negative. So that becomes this part. Okay? And then that cycle just repeats from here to this point. Really, it is this point that everything is negative. Okay. And then at that point, your current becomes positive, but your voltage is still negative. So from that point to let's see, to this point, is still going to be negative, and then beyond that point, right? Now in this region right here, that's not entirely correct. Let's kind of come back here and look at this. The idea is correct. I just don't have my boundaries correct. So they're both positive right here in this region. And then from that region to that region, it will be negative. And then from that region to this region, they're both negative right in here. So negative times a negative gives you a positive, right? So that's this part right here. There we go. And then that cycle just repeats. Okay? So it's fairly easy to see with that logic that the time average should be 0, right? Because your current and your voltage are sometimes going to be in the same direction, and sometimes they're not. So when they're not, their product is going to be negative, and when they are, they're going to be positive. And the time average of that, since it's cyclic, should just be 0. And then the same thing is going to hold true for the inductor, okay? But what about the power source? Okay, so what about my AC source? So let's take a look here. So my current through the circuit is I naught sine omega t minus phi. And my voltage of my source is V naught sine omega t, right? Okay, so notice that we can now take the time average of this product, right? Okay, so our time average is going to be this integral, but, okay, we're going to use a trig identity that says sine of A minus sine of B is equal to, this is your sine omega t times cosine of phi minus sine of phi times cosine of omega t. Okay? So we're going to put that into our integral. And I'm going to go ahead and group my I naught and V naught together since they're just constant. And so we're going to have sine of omega t times cosine phi minus sine of phi times cosine of omega t times sine of omega t. So all of this turns into this, and we still have our sine omega t left over, dt. So this splits up into two integrals. So first things first, if I distribute this sine omega t through, I'm going to get cosine of phi times sine squared omega t, and then minus a second integral, which is going to read sine of phi times cosine omega t times sine omega t. Okay. And so this first integral well, we've already done this integral a few times, right? And notice I brought cos phi out because this is a constant. Because phi is fixed as the phase constant, then cos phi is a constant, and it can be pulled out of the integral. And this just goes to 1/2, right? And same thing, sine of phi is a constant. So this comes out of the integral. But by the same logic that we just argued for the inductor and capacitor average power, sometimes this product will be positive, sometimes it'll be negative, but the average of the two is 0. And if you don't believe that, you can just plug that into Wolfram Alpha. Okay, just type in, go to Wolfram Alpha and say integrate sine x cos x from 0 to 2 pi. Okay, and you'll see that it's 0. Or go to Integral Calculator or something if you're not convinced of that. Right. So what this means is all of this boils down to so this integral is 1/2 the period. So this becomes I naught V naught over t times cosine phi times 1/2 t. So the t's are going to cancel out, and you're going to be left with cosine phi, but you're also going to be left with this 1/2. So 1/2 I naught V naught cosine of phi. Okay, so this is the average power delivered by the source, right? So this could be your outlet, this could be a function generator, whatever the case may be. And if we compare and contrast that to the previous formulas of 1/2 I naught V naught, average power here, you can kind of get a sense of what's going on. So with your resistor, the reason your resistor is never 0 is because the resistor doesn't care what direction the current is running through it. It's just going to get hot and release heat. Okay, so or if you want to model your resistor as like a light bulb, right? Then yeah, it is going to lose heat, but it's also going to produce light, right? So your light bulb doesn't care what direction the current is traveling. It's just going to get hot, produce light, and be done. Okay, so that's why that value is constant. Your capacitor and your inductor, the voltages and the currents are constantly shifting direction with respect to one another. And so sometimes their products are positive, sometimes their products are negative. So again, what this means is that energy is being put into these systems. And then, well, let me put it this way. Sometimes energy is being put into the systems, and sometimes they're releasing it. So their average power is zero, because in some cases the energy is positive, the energy transfer is positive, and in the other cases the energy transfer is negative. And you put all of that together and you get the power from the source. 1/2 I naught V naught times the phase angle. Okay? So when you put all of these together, then you will have that phase angle into your calculations. And note that this reduces if cos of phi equals 1, which implies that phi equals 0. And if phi equals 0, what that means is in that case, both of those are equal to 0. And what that means is you don't have a capacitor or a inductor in your element, or in your circuit rather. Okay? So if the cosine of phi goes away to 1, then that will typically mean that your inductor and capacitor either don't exist, they're not in the circuit, or your circuit is at the resonant frequency. Okay, so note that. Okay, so that is power. And now to wrap up, we want to talk a little bit about transformers. So a transformer is typically not much more than some sort of iron core. Okay, so imagine this is a piece of solid iron. Okay, and let's suppose that I wrap a coil around one side and I wrap a coil on the other side. Okay, now suppose that I have an AC signal of current in this wire. So my current is just constantly reversing directions, right? Well, instantaneously, the magnetic field from this coil is going to look something like this, but it's then going to have those fringe effects. And so what you'll get is outside the coil, this is going to produce those butterfly loops, those butterfly wings. Okay. And so the reason that you typically use iron as what we call the core, okay, is iron is highly magnetizable. So as the magnetic field from the first coil, or what we call the primary coil, is changing, well, its instantaneous magnetic field is going to be increased by the iron as it magnetizes the iron, and then there's a little bit of a feedback property where the iron is now magnetized due to the magnetic field of the coil, and that intensifies the overall magnetic field, and that increases the flux through this secondary coil. But if this is an AC current, okay, then what that means is this flux is changing, because at one instant the magnetic field will be polarized like this, and then the magnetic field will die off, and then it will be polarized like this. Okay? So it's just constantly flipping back and forth between these two, so that flux is changing through the secondary coil. And so you get an EMF from Faraday's law. Okay? So that induces a voltage in your secondary coil. So we're going to label this the primary. Okay? We're going to label this the primary. And we're going to say that the primary has NP turns. And it's held at a potential difference of Vp, and the current running through it is IP. Okay? Now, the entire point here is that you can adjust what your current and your voltage is in this induced coil, or what we call the secondary. So our secondary has NS turns, and it will be held at a voltage Vs, and it will have a current Is running through it. Okay? But so the entire point is that because your EMF is proportional to the number of turns, that means that the voltage of your primary is proportional to the number of turns of your primary, and the voltage of your secondary is equal to, or proportional to, rather, the number of turns of your secondary. And so this leads to a very important result, okay? And that is that the number of turns, let me make sure that I get this right. So, yes. Okay. The voltage of your primary to the voltage of your secondary is going to be equal to the ratio of the number of turns in your primary, to the number of turns in your secondary. Okay, so what this means is that we can calculate the potential in the secondary coil by solving this ratio. And so the potential in the secondary coil is going to be equal to the potential in the initial coil times the ratio of NS over NP. Okay? So, if NP is greater than NS, then this is what we call a step down transformer. And you can see that if this is the case, then this ratio is going to be less than 1. And so that means that Vs is going to be less than Vp. Okay? But if NP is less than NS, then this is a step-up transformer. And this ratio NS over NP is going to be greater than 1. Okay? So, for example, suppose that in this particular case, so let's actually kind of think through an actual power station, right? So an actual power station, where your power is generated, your potential is often going to be on the order of 10 to the 5th volts or more. Okay, 100,000 volts. And let's say it gets stepped down to a voltage that we don't know. Okay, but I know that my NP, let's say I have 1,000 turns in this first primary coil. And my NS, I have 100 turns. Okay, so I want to solve for the value of the voltage in this secondary coil. Okay, what I can do is I can come right here and I can say that Vs is going to be equal to 10 to the 5th times this ratio of 100 to 1,000. So this is 0.1, and 0.1 times 10 to the 5th is 10 to the 4th. So I've stepped down this voltage from 100,000 volts down to 10,000 volts. Now that's still quite a bit, okay? That's still quite a bit, but you get the picture, right? When I have a fewer amount of coils in my secondary, then the voltage steps down. But if I have more coils in my secondary, then my voltage steps up. Now, that immediately begs a question. Okay, why, if we can step voltage up, why can't we just step it up as much as we would like and then send that voltage to everywhere in the world? Why can't we just solve the energy crisis? Okay, and the answer is energy conservation. So energy conservation demands that the power delivered by the primary is equal to the power delivered by the secondary. So I primary times V primary must equal I secondary times V secondary. And so with this, if let's say we built a step-up transformer so that my primary voltage was less than my secondary voltage, what that means, the cost is that my secondary current is less than my primary current. So even though I can step up the voltage arbitrarily as high as I would like, I can't necessarily draw more current from that voltage than the power being delivered by the original circuit. Okay. So that is the cost. That is why we cannot just infinitely step up, even a 1.5 volt battery, right? If energy conservation weren't a thing here, then in principle you could step up a 1.5 volt battery and just keep stepping it up and just keep drawing power from it. But that doesn't make any sense. And if you think about it, it shouldn't make any sense because let's say you take a AA battery and you just keep stepping it up, stepping it up, stepping it up, stepping it up. That battery is going to have to supply more and more and more and more and more and more current. But what do batteries do? They use their charge and then they die, right? They're no longer usable unless they're recharged. So you can't get energy for free, okay? So even though a transformer is a really good way to mitigate voltage or control your voltage, you can't get free voltage, okay? That is the point. So with that in mind, we will leave AC circuits here and we will see you in the next topics.